For each of these problems, we're going to identify the points of discontinuity. We're going to state the reason that we know that that particular value is a discontinuity. And we're also going to classify the discontinuity as either removable or non-removable. When it comes to rational functions, such as what we see in example A, there are basically two main spots where we're going to have our discontinuity, and that's going to be at your domain restrictions, specifically for holes and for vertical asymptotes. So we're going to start to look for those. Here we're going to factor the bottom portion of our expression here. And we do see that there is a factor that's going to cancel out. So from what we have left, we can see that there is going to be a hole located at x is equal to -2 because of the canceled factor. And we can see that there's going to be a vertical asymptote at x is equal to +4 from what's left over in the denominator. So those are our 2 points of discontinuity. So we're going to say there is a discontinuity at x is equal to -2 because, and the reason we know that this particular point is a point of discontinuity is because at a hole, the actual point does not exist. So we are not meeting the second condition of f of c exists here. So we're going to say f of -2 does not exist. This is a removable discontinuity. The reason that this is considered a removable discontinuity is because the limit still exists. The very first condition to be continuous is true, and that classifies it as removable. We're going to do a very similar setup for the vertical asymptote, but with slightly different reasons. So at x equals 4, there is a discontinuity because the limit as x approaches to 4 does not exist. This is considered to be a non-removable discontinuity since the limit does not exist. Our next example is a piecewise function. So for piecewise functions, there are 2 main places where you want to be looking for discontinuities. The first is going to be when we are examining the domain restrictions on each one of those pieces. Anytime we transition from one piece to another piece, there is the possibility of having a discontinuity. The other aspect that you also want to investigate is each of the functions that appear in your piecewise function. If those functions ever have a point of discontinuity like a hole or a vertical asymptote like we just examined, we want to also include that in the list if it applies. In this particular case, when we're dealing with a quadratic equation, we don't have to worry about discontinuities. Linear equation, same thing. Exponential equations, we don't have to worry about discontinuities. So we're really just going to focus on the places where we transition between each piece, mainly x is equal to -1 and also x is equal to 2. So we want to check that the 3 conditions for continuity apply at each one of these points. So we'll start with x equals 1, and we're going to check to see what the limit as x approaches -1 of our function g of x is going to be. Now we're going to have to look at the left and the right-hand limits. So we're going to have to look to see if the limit as x approaches -1 from the left, which would be the piece of x squared minus 2x plus 1, would in fact be the same as the limit as we're approaching -1 from the right-hand side, and that would be the x plus 2 piece, the linear piece. So we're going to use some direct substitution and see if these limits are equal. So as we can see, the limit on the left was approaching 4, and the limit on the right approached 1. So that means that this limit does not exist. So we're going to conclude that there is a point of discontinuity at x equals -1 because the limit doesn't exist. And this would be classified as a non-removable discontinuity. So now we're going to investigate what happens at x equals 2. And again, the first thing that we're going to examine is the limit as x approaches 2 of our function g of x. So we'll look at the left-hand side, and that will be our linear piece x plus 2. And we're going to see if that's the same as the limit on the right-hand side, which would be the 2 to the x power exponential function. So we're going to do our direct substitution. And we get 4 is equal to 4. So here we know that our limit does exist. So that is the first condition for continuity. Our second condition is to ensure that we also have a point or a value when we are at x equals 2. So if we try to evaluate what g of 2 is going to be, we're going to take a look back at our function and see that we do have an equal to sign for when we have 2, and we're going to use the 2 to the x function to evaluate that. So that is going to be 2 squared, which is equal to 4. And our last condition is to ensure that the limit and the point itself have the same value. So we're just ensuring that the limit as x approaches 2 of our function is the same as g of 2 of the function, which they're both equal to 4. So we would know that g of x is continuous at x equals 2. Our last example is looking at a graph. And again, we want to identify the points of discontinuity as well as the reasons why they are discontinuous and whether it's removable or non-removable. So we're going to start working our way from the left. And as we approach the value of -2, we see that we're approaching a vertical asymptote at x is equal to -2. That is our first point of discontinuity. Since the limit does not exist, this is considered a non-removable discontinuity. So we have a non-removable discontinuity at x equals -2 because the limit as x approaches -2 of f of x does not exist. So remember, we're not saying that it's because there's a vertical asymptote there. We're using the definition of continuity as our explanation for why this is discontinuous. Our next value, if we kind of continue to follow along, is going to happen at x is equal to 0. Again, here we had a non-removable discontinuity at x equals 0, and it's because the limit, again, as we approach 0 of our function, does not exist. The left and the right-hand limits just don't agree on a single value. Our third location, if we continue to follow this function of a point of discontinuity, is going to happen at x is equal to 2. So here at x equals 2, we have a removable discontinuity, and that's because the limit as we approach 2 does exist, but the point does not. So this is a discontinuity because our point doesn't exist there, and we would classify it as removable because we still do have a limit.